Good morning. Welcome to VSPG. Today we have Åke. You can go ahead and share your screen. Today we have a presentation from Åke Johansson titled "Things You Can Do from Home During a Pandemic: A geochronological review of magmatism along the external margin of Columbia and in the Grenville-age orogens forming the core of Rodinia." Next week, we will hear from Ronnie Schoenberg from the University of Tübingen. And that talk is titled "Mode and Timing of the Oxidation of Early Earth's Atmosphere, Geosphere, Hydrosphere System." That's next week. So with that, Andre is going to go ahead and introduce Åke for us today.
Yeah, it's a great pleasure to introduce Åke Johansson, and especially he was able to step in to replace our speaker in last minute, so we really appreciate it. Åke was born and raised in Stockholm, Sweden, and studied in Stockholm University under David Rickards in our research group, and with PhD thesis on lead zinc veins in Sweden. After it, he worked in Swedish Museum of Natural History in Stockholm, working in isotope geochemistry group. And most of his research was based on Precambrian geology and evolution of Finno-Scandian shield, and he applied uranium-lead geochronology, strontium, neodymium, and hafnium isotope geochemistry, as well as major and trace element geochemistry of various magmatic rocks. And outside of Sweden, he worked on Precambrian and Caledonian rocks of northeastern Sweden with Professor David Gee, and also with Svetlana Bogdanova on Danish island of Bornholm. And later, he developed interest in position of Finno-Scandia and Baltica in general in picture of Proterozoic supercontinents and connection to Amazonia and West Africa. And he came with acronym Samba, which stands for South American Baltica sort of reconstruction, but still people argue about. And working in Swedish museum, he also did a lot of outreach work, and he retired in 2022, but he continues as an associate researcher at the museum and working on a sort of popular book on geology for Swedish general audience. So this talk that he will present today is based on what he and our large group of people done during pandemic, and it was published in Precambrian Research, I think, a year or two ago. So with this, I pass it to Åke.
Okay, thank you, Andre, and thank you very much for all of you for coming here and listening. So yeah, you see the title of the talk, a chronological review of magmatism along the external margin of Columbia and in the Grenville-age orogens forming the core of Rodinia. First of all, sometimes when I give talk, people ask, where do you work? You are in university, or where is it? So I started by showing this picture of the Swedish Museum of Natural History, or Naturhistoriska Riksmuseet, as it's called in Swedish, in Stockholm. The museum building is from 1916, so a few years ago we had our 100th anniversary in this building. I haven't been there that long. I've been there since 1984, but that's quite a long time, that also. So I said that there are many others involved in this work. So in this paper that we published in Precambrian Research, we were 22 or maybe 23 authors, including myself then. So I took the initiative, you can say, and tried to correlate the work and have everything written down. And then we were dividing it up. So what I call here Team Baltica, me trying to put the age data from Sweden together, or actually there was an age database from the Geological Service, so I only had to sort of go through and work with that. And the same with Finland and Hannu Humma in Finland, Bernard Bingen from Norway, although he's Belgian originally. They also had already a Geological Service age databases that they could work on. And then there were Alvar Suoso from Estonia, Gersina Skrilaiter from Lithuania, Eva Krzyminska. I apologize for all pronunciations that are maybe not correct, but anyway, from Poland, and Leonid Shumliansky, who many of you know from Ukraine, taking care of the Ukrainian and Belarusian data. And then we come to Laurentia. And first of all, I almost forgot the south tip of Greenland, but then I remember them. So I had Todd Waite and his student Rikke Vestergaard in Copenhagen, taking care of southern Greenland. And then it was some problem to find people on the Laurentian side, but through Kent Condy, I got in contact with Mark Holland, who took care of Western and Central United States, and Chris Holm Denoma, who took care of Eastern USA and Canada, the Grenville Belt. And in Amazonia, I had contact with Wilson Teixeira, and he in turn had contact with Frederico Faleiros and Bruno Ribeiro, teamed up and assembled the Amazonian data. And that was like the original plan. And then I started to think about maybe we should have Kalahari as well, if Kalahari is coming and colliding with Laurentia. So I got in contact with Joachim Jacobs in Norway. He's German, but he lives in Norway. And his student, Cheng Wang, who is Chinese, but was in Norway at least at that time, who are doing research in Southern Africa and Antarctica. So they formed Team Kalahari together with Bob Thomas and Paul Macy from South Africa. And then I had some contact with Chris Kirkland, who was a postdoc at our lab several years ago. So he's in Western Australia together with Michael Hartnady. So they assembled data from Western Australia. And then there is Bruce Eglinton from Canada, who did a lot of the database management and helped with plate reconstructions and especially animation that you will hopefully see towards the end. And our man in Hawaii, Steve Putz, who I think he's not geologist. I've never met him, but I think he's mathematician and a statistician. And he's a friend of Kent Condy. So through Kent Condy, I got in contact with him. So he could do a lot of these statistical things and that database management also, and Google Earth plotting. He's worked with Kent Condy on these gigantic uranium-lead databases and hafnium isotope databases and see trends and so on in that. So a big group of people, and the work got published in this special volume in Precambrian Research in memory of Svetlana Bogdanova. So there is that publication. So you have the link there if you want to have a look and haven't seen it yet. So everything I'm going to talk about is like it's published, and I have given a similar talk at the IGCP 648 seminar series 1.5 years ago. So if you have seen that and heard that, you can maybe in California, you can go and have coffee and start working instead. And if you are here in Europe, you can go and have dinner. But otherwise, you are welcome to continue to listen. So I promised to Alex and Andre that I should give a kind of background about the Samba model, my Samba model. And since maybe not everybody knows about it, or people can wonder what is the status, what are the objections, and so on. So it started in 2009, or at least my first publication then in 2009. That was just on my own then. And then a follow-up publication also in Precambrian Research in 2014. And in between them, there is also an extended abstract, 4 pages from 2013. It was an geological meeting here in Uppsala in Sweden in 2013. And I wrote an extended abstract, which probably not very many have seen, and not very many came and listened to the talk in Uppsala either. But I thought I put it here as well, so you may try to find it or ask me, and I can send it to you if you're interested. So I guess all of you know that there have been many others, or several other supercontinents before Pangaea. There was Rodinia, Columbia, Onuna, and maybe or maybe not Kennerland before that. My starting point when I was getting interested in supercontinent reconstruction was when I was working with Svetlana Bogdanova and others on the Mesoproterozoic A-type granitites on the Danish island on Bornholm in the southern Baltic Sea. You see down here, and Bornholm is the southernmost exposed tip of the Fennoscandian shield. In that way, it can say it's a bit strategic. It's located along the Tornquist zone or Trans-European suture zone, which forms the southwest border of the Fennoscandian shield. So when we were standing there and discussing the tectonic setting of these granitoids, then quite naturally the question come up, what was on the other side of this Trans-European suture zone in the Mesoproterozoic when Western and Central Europe were not there? Was there an ocean? What would happen if we would step out in that direction? Would we fall into the ocean, or was there another continent instead over in that direction? You have all seen this Rodinia reconstruction from Lee et al. 2008, and as many Rodinia reconstruction, it has Amazonia somewhat loosely attached to the southwest side of Baltica in Rodinia. And they see the Grenville origin as a result of collision between Laurentia, Baltica, and Amazonia. But then we started to think about what was the situation further back in time. When you go back into the Mesoproterozoic in the Columbia or Nuna supercontinent, was there still a connection between Baltica and Amazonia? So I copied various geological overview maps that I found of Baltica, Amazonia, also Laurentia, West Africa, tried to copy them at the same scale and redrew them with the same kind of color scheme. And then I started to play around with them at the kitchen table at night when the kids had gone to sleep. Now they are big, the kids, so they have moved out of the house. But the kitchen table is the same. The view is not quite the same. The forest has been replaced by some new houses there, so unfortunately, but otherwise. So you can see, you can do some quite important research at the kitchen table. Sometimes you don't need a whole lab for that. And then to make sure that the pieces were the right size and that the reconstructions worked on a round globe and not just on a flat kitchen table or a flat computer screen, I glued them onto a globe I had at home. I had no experience in working with this G-Plates software. I tried to learn it from Johanna Salminen when I went to Finland, but I never quite mastered it. So I had to work in this very manual way on a real globe instead. For practical versions on the Northern Hemisphere, because it's easier you have gravity on your side there. It's more problematic if you try to work on the Southern Hemisphere. Gravity is working in the wrong way for you. Sun is also, I discovered when I was in Brazil that the sun is moving also in the wrong direction on the sky. It's moving backwards on the Southern Hemisphere. So it's much easier to work here up in the Northern Hemisphere. So this shows the Columbia, Onuna, Samba configuration. You see Sweden there, Fennoscandia, Baltica, Amazonia, West Africa, and then at least a part of Laurentia over on that side. And then if you move to the Rodinia configuration, Baltica, Amazonia, West Africa have turned around and collided with Laurentia on the southeastern side of Laurentia. So something like that, I would imagine at least. So then I needed some kind of catchy name. So an acronym, Samba models for South America, Baltica, and maybe a nice catchy picture with this nice looking Brazilian, I suppose, girl that I found on the internet. Her nice Samba outfit. So in my view, comparison of Baltica, Amazonia, and West Africa geology suggests that the northern side of Amazonia was attached to the present southwest side of Baltica, the Tornquist margin. So Amazonia was sitting where now Central and Western Europe are sitting in relation to Baltica. and that the present-day west coast of West Africa was attached to the southern Black Sea, Caspian Sea margin of Baltica. And then you had an active margin out here in the present-day west. And this configuration started already at, say, around 1800 million years with the assembly of Columbia or Nuna. And this configuration, my model is solely based on geological or geochronological evidence, not any paleomagnetic evidence. I've never worked with paleomagnetics, so I try to read and so, but I have very difficult to follow and evaluate. Often the evidence seems to be very contradictory and confusing to me, so I only base myself on what the geology says. And then, as you know, to the northern side, Baltica was attached to Greenland, Laurentia here, Charlie Gower's Nena configuration, Northern Europe, North America configuration, which is supported by paleomagnetic evidence, and maybe to Siberia here on the northeast side. And then with rotation, you get to the Rodinia configuration, rotation of combined Baltica, Amazonia, West Africa landmass, around 150 degrees in total, but maybe that's relative to Laurentia. So Laurentia may have moved, say, if Baltica, Amazonia, West Africa moved 90 degrees, then Laurentia moved 60 degrees in the opposite direction. And collision with the southeast Grenville margin of Laurentia, forming the Grenville-Norwegian Sundsas orogens. So in my view, there was no Grenville-age collision between Baltica and Amazonia, although you often see that in reconstructions. In my view, they remained fixed together with West Africa in the same relative positions in Columbia and Rodinia. So all in all, the Baltica, Amazonia, West Africa connection, as I see it, lasted for at least 1 billion years, from 1800 to at least 800 million years, and perhaps to the final breakup of Rodinia at 600 million years. So I had my son, when he had been grown a bit older, to make this animation for me to show this rotation from the Columbia to the Rodinia configuration. And here, for simplicity, Baltica, West Africa, Amazonia, they are rotating, I think, 75 degrees clockwise, and Laurentia, Siberia, 75 degrees counterclockwise. So it's just a relative rotation. So just for simplicity, I put the same number. So that was it. The Samba configuration finally broke up with the breakup of Rodinia, as Baltica separated from Amazonia and West Africa, as well as Laurentia at 600 million years, and started its independent northward journey up to here where it's now. So what about objections or support for this model? Well, the objections have mainly been then from paleomagnetic people, since I didn't really take their views into consideration. So one objection was that in my original 2009 paper, I had put Northwest Baltica, well, Northwest Norway, you can say, in a very tight geological contact with Southeast Greenland, leaving a gap between Eastern Greenland and Northern Baltica up here. But the paleomagnetic experts, the people there, complained and said that there was consistent paleomagnetic evidence that Northern Baltica was instead attached to Eastern Greenland, as here in this B option, leaving a gap between Western Baltica and Southeast Greenland. So this figure is from my 2014 paper, where I discussed both these options, the pros and cons, and didn't really take a stand there. But later on, since it seemed that for once the paleomagnetic evidence was very consistent, I followed the paleomagnetically based option B. So in this 2022 paper, we are following that option. But from my point of view, from a Samba point of view, this is a side issue. This is a question of the Nena configuration between Northern Europe and North America, and not really the Samba configuration. So when it comes to the Samba configuration from Amazonia, there is apparently some paleomagnetic support from Northern Amazonia, from the Guyana Shield, for a connection to Baltica at 1790 million years, the Avanavero seals there, and also at 1540 million years, the Muku-Chai complex. But then from southern Amazonia, from the central Brazil shield, there are several other paleomagnetic poles which seem to diverge and don't really agree, and especially these younger ones. So one possibility would be that there would be some kind of big shear zone translation between northern and southern Amazonia along the Amazonas basin. But since orogenic belt seems to continue across there, it doesn't seem like a very likely alternative. Or maybe there is some kind of rotation or tilting of the southwestern part of Amazonia. I don't know. Or yes, but to the paleomagnetic people, they say that the Samba connection could be okay from 1800 to 1540, but sometime between 1540 and 1420, there was some kind of shift in between Amazonia and Baltica. But I don't really see any geological evidence for that, any signs for that. So I'm a bit skeptical towards the paleomagnetics. Otherwise, many Brazilian geologists, they are positive to a long-lived Baltic-Amazonia connection on the geological grounds. But it's very difficult. You're never going to prove or disprove such a connection by finding some very definitive geological evidence. But this is a rock that proves it or not. That's not going to happen. The same with relations between Amazonia and West Africa. Maybe I was thinking about this now, that the best bet would perhaps be if there are some dike swarms that going across from one craton to another, where you can see that it's the same age and the same geochemistry and the same paleomagnetic characteristics. That would really give some kind of piecing point that could almost prove the Samba connection or not. But according to Sergei Pisarevsky and then according to paleomagnetics, he doesn't like the Samba connection really. He wants Amazonia and West Africa to not to be part of Colombia, to be out somewhere to the west, out in the world ocean, forming an independent block. And instead he puts India next to Baltica, where I have Amazonia. So I know he and Svetlana, they gave a talk about that in an AG meeting. I wasn't there, so I asked them, could I send me the talk, but I've never got any. So I don't exactly know what the evidence is here. But I guess you can play around at least with the longitude of India and Amazonia very much so. Here is some more support. Terentiev and Santos in 2020 in a paper in Earth Science Review. They studied Sarmatia and West Africa and suggested that there was a connection between Sarmatia, the southern Baltica, and eastern Amazonia and West Africa that went back already to the earliest Paleoproterozoic, even Archean times, before Colombia existed. This is similar to what I said in this Geological extended abstract in 2013. So I agree with them, but they agree with me. Then there was a paper by Gong et al. In Geology in 2021, where they flipped West Africa 180 degrees around based on two new paleomagnetic poles from inliers in the Anti-Atlas Mountains in Morocco. And that would disrupt all previous geological correlations between West Africa and Eastern Amazonia, and also between West Africa and Baltica. So I don't really like to believe in that, because it would disrupt the Samba model as well. But it's very difficult for me to evaluate that and compare that to other paleomagnetic evidence. That I have to leave to the paleomagnetic people. So that was a bit introduction about Samba model and pros and cons and whatever arguments around it. Now turning to the new study. Here you see partial Columbia reconstructions at say 1590 million years, including Nena and Samba, and also Proto-Sweat fit of Australia on the other side of Laurentia. So we will focus on what Kent Condy has called the Great Proterozoic accretioner Orogen along the external Laurentia Baltic Amazonia margin of Colombia. What is colored yellow and light brown here. The yellow areas, they are 2000 to 750 million year Orogens, so what you can call Proto-Columbian Orogens if you want that. And the light brown, they are dominantly 750 to 1300 million years Orogens. Those are the formed during the existence of Columbia, Columbian, Columbian orogens. So I'm here. You are out somewhere there in the rest of the world. This is a Rodinia reconstruction at 900 million years, including then Samba configuration. And here we focus then on the collisional Grenville, Norwegian, Sunsas, Namaka, Natal, Albany, Fraser, orogens in Laurentia, Baltica, Amazonia, Kalahari, and Australia, respectively. Proto-Rodinian orogens, we suggested in the paper that you could call them if you would have like to have some overall name other than just say Grenville-age orogens. So the areas that are pink in the center of Rodinia in this reconstruction. So we took published magmatic uranium-lead zircon ages, plus a few monazite, titanite, badolite ages that we compiled from already existing databases and other previous compilations. And in some cases, people had to do a lot of manual compilation as well. So these are uranium-lead data by TIMS, SIMS, or LA-ICP-MS methods. We did some filtering, so we took away ages that have larger uncertainties than plus minus 20 million years old, rather imprecise ages that you don't want to keep to will blur the results maybe. We also took away dolerite dike swarms and rift-related volcanics like the Kivanawan rift and so on, because we are mainly interested in the growth of continents and orogens and origin-related magmatism and not breaking the continents apart. The age range from 2,300 to 800 million years, so covering the age span of Columbia and the assembly of Rodinia. And data from along the active external margin of Columbia, the Great Proterozoic accretioner orogen, in Baltica, in Laurentia, in Amazonia, from 1800 to 1260 million years, but not internal conditional orogens in Columbia, so not the Trans-Hudson, not the Lapland Kola belt in northern Baltica. And then the subsequent Grenville-age collisional orogens forming Rodinia in Baltica, Laurentia, Amazonia, and also Kalahari in Western Australia. And for the final diagrams, the age data have been normalized by Steve Putz according to the surface area of the corresponding geological provinces to compensate for uneven sample density. So if I start in my own part of the world in Baltica, we had 922 data records from there, from the Karelian province up in the northeast, Svekofenian province, Trans-Scandinavian igneous belt, Sveko-Norwegian province, and the concealed basement in the Baltic republics, northeast Poland, and the western part of Sarmatia in Ukraine and Belarus. And also magmatism in intraplate magmatic provinces, shown by these orange lines on the map in Sarmatia in Ukraine, around 1800 to 1750 million years. The central Fennoscandian Rapakivus around 1650 to 1500, and slightly younger in southern Fennoscandia from 1550 to 1400 million years magmatism. And the data from Baltic and the other continents were plotted on Google Earth maps by Steve Putz and color-coded according to age. You can see the age division. It's the same on all the maps that we sort of agreed on. So to say, yeah, all they have been arranged in similar ways. So data are plotted as relative probability curves on the left-hand side, divided up into different geographic areas and orogenic provinces in the left-hand diagrams. The heights of the diagrams proportional to the number of data records. And then to the right, you have cumulative plots featuring individual data points subdivided in the same way. And the direction of time is reversed. You can note that here it's like age going from youngest to oldest, but here it's more like time going from left to right, from old to young. That seems more natural, at least to me as a Westerner. You read from left to right. So maybe if you were Arabic or so, you would think it's more natural to go from right to left. But for me, I think time going from left to right is more natural. intraplate magmatism has been plotted within the orogenic provinces where it occurs. So for instance, the Rapakivi granites in central Fennoscandia, they have been plotted within the Svekofenian province, although they are not related really to the Svekofenian orogeny, but they occur in the same area. So if, without going into too much detail, looking a bit on the exposed area of Fennoscandia here, you have multiple peaks of Karelian and Svekofenian magmatism here up in the Karelian province in the northeast. A lot of it is maybe more mafic extension related, but also Svekofenian magmatism in this area, starting from 2300 or even older and going down to 1800. Then you have this very large Svekofenian magmatic peak around 1880 million years, followed by a late magmatic peak at around 1800 million years. And then there's a double peak of Rapakivi magmatism, or I think even a third small peak here of Rapakivi magmatism at 1550 million years. The Trans-Scandinavian igneous belt, you have the TIB1 magmatism around 1800 that overlaps with the late Svekofenian magmatism. You have the TIB2 magmatism at 1700 million years, and then the younger A-type granites in southern Fennoscandia at around 1450 million years. And then you see the very long and complex evolution of the Svekofenian province starting at 1700 or even a little bit older here, but mainly from 1700 and over to 1900 million years. If you go to Laurentia, we have about 1200 data records from the Ketelidian province up in southern Greenland, and then the Makovik, Penocéan, Mojave, Yavapai, Matatzal, Granite Rhyolite, Grenville provinces. And as you know, over there are large parts of the central United States that consist of concealed basement, but there are quite a lot of drill hole data from here with the ages. We left out the Grenville-age inliers within the Appalachians because they could be exotic to Laurentia. Many people consider them as part of Amazonia left behind. So that will complicate issues, so we left them out. Intraplate magmatism has not been separated from orogenic magmatism in Laurentia. But here is the Laurentian data, again, curves here and these cumulative plots over here. So you can see the long and complex evolution of the Grenville province, including all the pre-Grenvillian evolution here, similar to the Circumnovidian province in Fennoscandia. The Larno province have been separated out because we wanted to compare that with the Kalahari data from the Natal-Namakwa belt. What stands out here in Laurentia is this North American magmatic gap between 1600 and 1500 million years. You see that in all the Laurentian diagrams. As with Baltica, there is nothing really new here. You all have, this is all old data, so it's just a compilation, but it's nice to see everything plotted together. You can compare the data internally in Baltica or Laurentia, and then in between the different continents and cratons. So going to Amazonia, we have 628 data records from the Guyana Shield up here in the north, the central Brazil or Guapore Shield in the south, and also this small Rio Apa craton, which according to the Brazilians is a small displaced part of Amazonia sitting down at the southern tip. And you have these different orogenic belts, starting with the Archaea nuclei and then going towards younger and younger towards the southwest here. Also, you have some intraplate magmatic provinces or silicious large igneous provinces outlined by the orange lines that the Brazilian geologists like to distinguish here. So here we plotted two diagrams, one for the orogenic magmatism with all the different peaks, and one for the what is considered intraplate magmatism. Here are the different provinces divided up in similar ways as in Laurentia, with the cumulative plots. And these gray shaded things, that's the orogenic events that has been marked, like here and here. The same in Laurentia and Baltica also, based on metamorphic ages and deformation. I made this special plot just to compare the organic magmatism and the interplate magmatism in Amazonia. So turn this upside down so you could more easily compare. So this that looks like icicles. That's the interplate magmatism then. And it looks like we have some kind of correlation here between the peaks, the organic peaks and the interplate magmatism. Kalahari, Southern Africa plus a part of Antarctica, 265 data points from the Magma Natal belt here in Namibia and South Africa. Falkland Islands, we're sitting somewhere here with a couple of points, and then the Maud belt in East Antarctica. And also Grenville-age up, not quite a lot up here in northern Mozambique and Malawi. Here the focus was on the Grenville-age belts only, not the earlier Paleo to Mesoproterozoic organic belts. There are some Paleoproterozoic inliers in the Namakwa sector in Namibia that were included, but not this larger Paleoproterozoic area. When we came to the end, we sort of regretted that maybe we should have included this as well to make the data more comparable with the Amazonia and Laurentia and so, but then it was a bit too late. So that will be something for a future project. But it means that the data are not fully comparable with the data from Baltica, Laurentia, Amazonia when you compare them. So Kalahari crater, these Paleoproterozoic inliers in Namibia in the Namakwa sector, and then the different organic events and magmatic pulses in the Namakwa Natal belt and in the Maud belt and in Malawi and Mozambique as well. You can see the different partly overlapping peaks over here. And we got to Western Australia, Albany Fraser Orogen, something called the Ukla basement, where there are drill cores, and then the Musgrave province in Central Australia. And again, the focus is on the Grenville-age belts plus some older inliers within the Albany Fraser Orogen, but not on the other older Paleoproterozoic and so on belts. And only from Western Australia, I think Chris Kirkland and Michael Hartnode, they are sitting in the Geological Survey of Western Australia, so they only had compilations from Western Australia. So again, we were a bit regretting and got criticism from one of the reviewers, Bill Collins, that we didn't include the rest of Australia as well. So, but something for someone else to continue on. So here you see a little bit of Paleoproterozoic and Mesoproterozoic data, and then you get to the from 1350 to say around 950, the Grenville-age peaks here, very sharp peaks with gaps in between here in the different provinces. So all the data plotted together, relative probability curve turned 90 degrees, and then I mirrored it, so I got this kind of nice diagram. The background colors are these periods that we agreed on to color code our data. So it's not like the Orosirian or Riacean or Staterian or Tonian. It's just our more random periods here. But we try to put division lines where there are like minimum in the magmatic record, so not to divide the peaks into different color codes. The red dotted line here, you see, that's the unweighted data, and the black line and the gray shaded area, that's the data that is normalized according to surface area of the respective geological province or part of Creighton. And that was what Steve Putz did to compensate for uneven sample density, because of you have some well-exposed and well-studied areas, shield areas like here in Fennoscandia, and then you have some remote, less studied areas or areas that are covered by younger sediments or ice like in Greenland, Antarctica, or water like the Baltic Sea. So try to compensate for that. It's not a very dramatic change if you compare the red line with the black line, but you can see that this very prominent 1880 million year peak from Fennoscandia and also from Amazonia is considerably reduced, but it's still the highest peak. Some peaks like the one in 1770 and 1440, they are instead increased with this normalization. But still, the most prominent peak is the one at 1880, followed by peaks at 1770 to 1800s, and here at around 1760, 1700, 1440, 1470, short, sharp peak at 1370. And then you have the Grenville-age orogens showing up as a wide composite peak, broad overlapping peaks from 1200 to 950 million years or 900 million years, with a culmination at around 1080 million years. And if you divide that up into the different continents or cratons, you can see that the oldest data we have, they are mainly from Amazonia and a little bit from Karelia here also. The peaks before 2000, also this very prominent 990 peak, both in Amazonia and Baltica. And then we have peaks at 1880 and 1800 to 1760, both in Baltica and Amazonia. So it's quite a good overlap here. Laurentia starts to come in. It's a bit slow starter here, so it starts to come in at 1850 million years, and then it's a lot of activity here at 1780, 1700, 1660. And then you have the magmatic gap here at 1600 to 1500, but that has no counterpart in Baltica and Amazonia. Instead, you have quite a lot of activity here in Amazonia, just around 1550 million years. And then there is activity again in Laurentia, this very sharp 1370 peak, also in Amazonia. Baltica is not so visible here. I guess it has to do with the normalization also, that this second Norwegian province is quite a small surface area, so it gets quite a lot reduced here, although there's a lot of data from there. And then you have the Grenville-age peak starting here at 1250 or 1200 and going down, mostly from Laurentia and the Kalahari. Not so much, well, you have it in all here, but they are not so prominent. And if you look at the cumulative growth curves of the same data, you very clearly see that the strong similarity between Amazonia and Baltica, much more than between, say, Amazonia and Laurentia or Baltica and Laurentia. Laurentia is a bit of a slow starter here, but it starts coming here. Then you have the magmatic gap here seen as a plateau here at between 1600 and 1500 million years. You don't see that in Amazonia or Baltica at all. Maybe here Australia a little bit, but Australian and Kalahari data you can't really compare because you left out much of the Paleoproterozoic here, so they are just much smaller data sets. So I have just stippled those lines. Shouldn't really compare them too much to the Baltica, Amazonia, Laurentia data. But then Steve Putz did some statistics here to show the correlations, and the best correlation then, as you could see, is between Baltica and Amazonia, 0.617. There are weak positive correlations between Baltica and Laurentia, and between Amazonia and Laurentia, and also between Australia and Kalahari, but nothing as prominent as the Baltica-Amazonia correlation. If you want to look at more regional comparisons, we look at Karelia and compare to Sarmatia and Eastern Amazonia prior to Columbia, say from 2300 to 1900 million years. Well, Kalahari was not joined to Sarmatia or Amazonia, so that was probably very separate. You see different peaks of largely mafic extinction-related magmatism. Sarmatia maybe was joined to Amazonia, but there is not very convincing similarity. Maybe if we had included more data from eastern and central Sarmatia, now we only included data from the western margin, so maybe there would be more overlap. There is some suggestion here at 1990 between this very prominent peak in Amazonia, this Orogens slip, and the Osnisk Mikashevich. I apologize to Andrei for the pronunciation. Igneous belt, Umib belt in Western Sarmatia. So at least Leonid likes to believe, and I agree with him, that maybe this Orogens slip is not really a slip, it's the continuation of this belt in Amazonia instead. But that you have to discuss with the Brazilians what they think. If you compare magmatism in the second Norwegian province in southwestern Sweden and southern Norway, and its Laurentian counterpart, the Grenville province in eastern Canada and southeastern United States, you see some similarities that are quite striking. The very marked Telemarkian peak in the second Norwegian province and the Pinvarian peak at 1500 in Laurentia, and also these Elsonian double peaks and Hallandian double peaks at 1460 and 1380 million years. There is overlap between the Pre-Norwegian and the Shawinigan peak at 1150. There is a magmatic lull at 1100 million years, but there are also less striking similarities or dissimilarities. The Laurentian magmatic gap you don't see in the second Norwegian province. There's a gap at 1200 million years in Laurentia that you don't really see. Well, there is a minimum, but not really a gap in the second Norwegian province. If you take just the Grenville-age Proto-Rodinian data from 1250 up to 900 million years and plot them on a separate diagram, and here the height reflects the number of data. There's very little data from Amazonia, from the Sunsas and Putumayo, so this became a very small diagram. Llano province again has been separated from the rest of the Grenville here to compare with the Kalahari data. You can see there are some similarity. One is there's this 1100 million gap in magmatism in all continents except Kalahari, where there is instead a peak. So this coincides, of course, with the Kivinavan rift, but that was not included in our compilation. But there is a gap here, except for in Kalahari, where there is instead a peak culmination in the magmatism around that time. But overall, I think you can say that the match between the peaks of the different cratons seems rather poor, and that is what the statistics says, according to Steve Putz also. So it suggests that different sites or different segments of this collisional origin were active at different times. Magmatic activity ceased at around 1,000 million years in Western Australia, around 950 in Kalahari and Laurentia, and around 900 million years in Baltica and Amazonia. Now we come to these animations, if we have time. Yeah, maybe. Animation that Bruce Eglinton did of magmatism from everything from 2,300 to 800 million years in Laurentia, Baltica, Amazonia, Kalahari, Australia, plotted on a present-day configuration of the world. So that was a data file that accompanied this paper, as can download it from Science Direct as a supplementary material. Now let's see. Yeah, now it started. It comes a bit of a legend. He included also from the other continents, not included in this paper, these small black dots, but otherwise the red dots are the ones from our compilation. So now it starts at 2,300. Some dot in eastern Amazonia and a little bit in Karelia now. Starting. And you also see some of these other black dots that were not included in our compilation, but he has his big database where they are included as well. Now there is some activity in what is now Ukraine, then Samothracia and Karelia and eastern Amazonia. Now now there's a lot of activity. Now it's a Svekofenon orogeny. You see whole Fennoscandia now is forming here, and the Trans-Scandinavian igneous belt, and also activity in Amazonia, and now it starts also in Laurentia. And also a little bit in Australia. We got, I guess, to the Gothial magmatism in southwest Fennoscandia. Some Rapakive magmatism in central Fennoscandia there. More activity in Laurentia and southern Fennoscandia. Gargar magmatism in southern Greenland. A lot in southern Africa and Australia and the Norwegian province and Grenville province. It's like a Norwegian province towards the end there. That's the end of it. And then I made a kind of animation using PowerPoint slides, where I also put the same data from Laurentia, Baltic, Amazonia, Kalahari, and Australia on a partial reconstruction of Colombia and Rodinia, but in a more coarser way in 50 million year steps. So let's see if I start that as well. Okay, so we start at 2,300. And actually, Laurentia shouldn't be joined, just so you know, it was not really a whole continent. I think I have a slightly different version, later version on the accompanying the paper, a supplementary material where I divided up Laurentia to make it look a bit more realistic. And also, I think I put Kalahari on the like in a separate box on the side here because you don't really know where it was located. But now we start to come to the Proto-Columbian Orogeny. So here we have all the Swecophenian magmatism here in Fennoscandia. And a bit later, and the Trans-Scandinavian igneous belt as well. And the late Swecophenian magmatism. There's quite a lot of activity here in southwest Laurentia and up here. I guess Labradorian magmatism here, I suppose. Bit of Rapakive magmatism here, a bit of Gothian magmatism there. And now we start to have breakup between Baltic and Laurentia. Although some say it was later around after 1120, so that depends how you interpret the paleomagnetics. But anyway, some breakup and rotation in opposite directions here. And final collision. Formation of the Grenville-age belts. Final magmatism seems to be here in southwest Baltica then. So summary and conclusions of all this. About 4,200 magmatic uranium lead ages between 2,300 and 800 million years have been compiled. They represent the active external margins of Laurentia, Baltica, and Amazonia in Colombia, and the subsequent collisional Grenville-age orogens in Laurentia, Baltica, Amazonia, Kalahari, and Australia. Magmatic peaks typically some tens of million years in duration, gaps in between. The strongest peak at 1880 million years is common to Baltica and Amazonia. Also, there are strong peaks at 1800 to 1760 million years, both in Baltica, Amazonia, and Laurentia. The Baltica Amazonia magmatic correlation is the strongest. The others are rather poor. That may indicate that Baltica and Amazonia share the same subduction system for considerable time, while the Laurentian margin formed a separate subduction system. That is a little bit like I've drawn on these plate tectonic reconstructions. So it's not a proof of the Samba connection, but at least a quite strong indication, I think, that Baltica and Amazonia share a lot of their history together. There are broad Grenville-age peaks on all continents from 1200 to 950 million years. But if you see more in detail, the intercontinental correlation is rather poor. The magmatism is diachronous. Magmatism ceased at 950 to 900 million years, as most areas became located inboard in Rodinia. At least if you don't believe the reconstruction of Trondslagstad et al., because they have a different model where the second region or Rodinia province is still on the outskirts of Rodinia. Suggestions for future studies, maybe complement, of course, with more paleo to Mesoproterozoic ages from Kalahari, and the same for the other parts of Australia to make those compilations more comparable and compatible with the Laurentia, Baltica, Amazonia data. Maybe do a bit more on our key and early Paleoproterozoic comparisons and correlations between Sarmatia, Eastern Amazonia, and West Africa. We didn't have any West Africa data at all, so look at the earlier history, the pre-Columbia history here. And then what about the Eastern Ghats belt of India? That would be, of course, also interesting to compare to test Sergei Pisarevsky's paleogeographic model, how that compares to the Baltica data, for instance. And then maybe data from other continents and cratons as well. But I leave that to others to continue with. So that's it. Thanks for your attention.
Okay, thank you, Aki. Great. So we'll go ahead and we'll start with question and discussion.
Yeah, I tried to see now. I see I felt a bit left out here because I wasn't looking at anyone. I minimized this, but now I can see that you are, at least some people are still there. That's good.
Yeah,
Kent
yeah,
Condi
I'd
is
say
also
about
there,
as
so.
many people who were there at the beginning are still here.
I was worried, sitting here all alone and worrying that I'm losing everybody.
Nope, everybody's still here. I have some things in the chat from during the presentation, so I'm just going to hit those, and then Bodo has a question. So first, Paul just pointed out that there's some magmatism from the Thalson Phelan origins around 2 billion Ray-Slave collision, and between 2.5 and 2.3 on the Northwest Ray Craton Aerosmith origin. Says Bruce Eglinton can provide details. That's probably all information that was in the animations you showed as well, or at least went into that. But maybe
no, it wasn't. That's the point. That's the point.
Oh, okay.
In the compilation, it indicates that Laurentia didn't have magmatism before about 1900, and that's completely incorrect. The Thelon Thalson, which is a 2,000 kilometer long origin, has magmatic history from about 1920 to about 2020.
Yeah, sure. What you need to remember is that in our compilation, we said that we are only concerned about the external margin of Laurentia, the great Proterozoic accretionary orogen. So we left all those internal collisional orogens, Trans-Hudson and Telson, whatever it's called, all those we left aside. They are not included at all in our compilation. Of course, Bruce Eglinton, he should have them in his big data file, but in our compilation we left all that out. So it's just the external margin of Laurentia that we.
I see. Well, then it entirely depends on the choice of the Nuna configuration.
Yeah, that's of course. But I think that is not so controversial to distinguish the internal and external magmatism of in Laurentia during Columbia times. Is that is purely sort of
Well, consensus
geographic.
doesn't always necessarily indicate truth.
That's true.
Okay. So I have one from K. Sunder Sarwan that said, would plotting all the data from each province into a Gaussian distribution and comparing curves of different provinces provide us similar insights to that of the cumulative curve?
Yeah, we made this relative probability curve, so they are like some kind of Gaussian, I guess. But well, I should have Steve Putz, because I don't really understand how his correlation calculations work. Really, you can intuitively see which curves match which and which look very difficult. But exactly to do the statistics, I don't have the capacity to do that. So it's something for Steve Putz, or it's something for. I mean, we have all the data that we have. That's also in an Excel file. That's supplementary material. You can see some of Steve Putz's calculations there in that Excel file, but anyone who is good in statistics can download them from the website from Science Direct and do their own statistics and continue to work on them. So I'll leave it with that.
Okay. Also, just really quickly, Nasser advertised the International Dike Conference and Large Igneous Province Conference, Rodinia 2023, coming up in May in Marrakesh, Morocco. And then let's go ahead and, Bodo, you can go ahead and unmute yourself and ask a question.
Yeah, hello, Åke, and nice to see you again. Well, we had these discussions for several times already.
Yeah.
Well, it's a huge collection of data, really. Congratulations, that's a lot. But anyway, you know, there are very many similarities between, or I would say even a complete match between the Sweco-Norwegian orogen and what we say the Grenville orogeny we see in Mexico and in northwestern Amazonia. There are not so many data, but well, the data are not included here. And the other thing, what we see, for some reason, there was a orogeny going on between 990 and 920 million years. And we see this, or you see this in the Sweco-Norwegian, and we see this in Mexico and in Northwest in Colombia. So something there was some collision going on at this time. For sure, we don't have a real proof that this happened between Baltica and Amazonia, but there's a complete match of the data for this time, and there's a large difference. At least if you look at all the metamorphic ages, there's a difference of at least 50 million years or 60 million years between the main collision, what we see in the Laurentian Grenville, and what we see in Sweco-Norwegian and Oaxaca Putumayo. So we need to explain this somehow, and what best matches is the collision between Baltica and Amazonia for this time. So maybe we should just open the ocean and close it again, but we have to do something here. So what is your opinion? How can we solve this?
Well, if you have seen the recent paper by Lee et al. In Earth Science Review 2023, they had moved Oaxaca, I don't know how to pronounce it really, Oaxaca. They had moved it from their old position in between Baltic and Amazonia. So now they had it between northwest Amazonia and Laurentia, or say, yeah, or just outside of the Sweco-Norwegian. So I think that would equally well qualify the similarities between, say, the Sweco-Norwegian and Oaxaca, or the Grenville and Oaxaca. But they didn't argue about it, so you have to check with them a little bit more what their arguments are. But I would prefer that, and not having Oaxaca squeezed in between Baltic and Amazonia, because on the Baltica side, we don't see any Grenville-age orogeny along the Tornquist line when you go down into eastern Poland or Ukraine on that margin. There is no sign of that. In that case, it should have all been rifted off. That's of course a possibility, but we don't see anything of that on that margin. And if you look at the Sweco-Norwegian orogeny, that's just on the southwest corner. It doesn't continue down into Poland or the Baltic republics or Ukraine or anything. And the tectonic transport in the Sweco-Norwegian orogeny, that's from the west or northwest, suggesting collision with Laurentia, not from the southwest as it would be if it was collision with Amazonia or Oaxaca. So I had a discussion the other day with Andre about this also, that we don't like to have your Oaxaca squeezed in between Baltic and Amazonia. Sorry about that. But you can be west of us, out in the west of Amazonia, west of Baltica. That's okay.
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 Thanks.
Paul, you want to go ahead?
Yeah, 2 points regarding Bodo's question about post-collisional magmatism in the Damra orogen, where the terminal collision is well dated at 550. Half the orogen is granite that was in place 50 million years later, completely post-collisional, completely post-structural. So I don't think you necessarily have to open up a new basin to get, post-collisional magmatism. Now, back to Åke's point, does it really make sense to talk about magmatism on the periphery of Nuna before Nuna had formed? Okay, so Nuna didn't exist until about 1850, and some people would put it 100 or 200 million years later. So in what sense, in what sense is magmatism before 1850 peripheral to a supercontinent that didn't exist yet?
No, I agree. It's not. We suggested in the paper to call that proto-Columbian. It's like the magmatism that is forming before Columbia
Well, the
is
point
forming.
is, why distinguish peripheral from internal when the supercontinent doesn't exist?
Yeah, then I mean, yeah, then you could mix everything, but at least it's the magmatisms that we included. It was in the same areas that later on become part of this great Proterozoic accretionary orogen. So say like the Svekofenian, that the main magmatism here is around 1880 million years. So that was really before Nuna formed, but it was part of the process that led to the formation of Nuna, at least, and later on the Svekofenian orogen be part of that external margin, you can say. But yeah, it's always we had some of this discussion. Where should we draw the border? Should we include the whole of Sarmatia? Should we include West Africa? Or Bruce Eglinton suggested, or should we include even older, or what should be excluded and what should be included? There's always some kind of problem where to draw the boundary for practical reasons also. But it may when you look at the Laurentian side, you can say that the action along the margin there really only started at around 1850, and say you have the Makovic, the Penokean, but that was really before Nuna had really aggregated, so they were like rather separate orogens maybe before Nuna had aggregated really.
Okay, Ian, you want to go ahead?
Yeah, fascinating compilation, Åke. Thanks for taking it all on. Was one question with regard to the 1100 million peak in Kalahari and the contrast to Laurentia. You said you excluded the Keweenaw in Laurentia, but did you include the Umkondo in Kalahari?
No, that's not included either. So
Okay.
no, so it's only like organic
real contrast.
granitic magmatism.
Yeah. Thank you.
All right. That exhausts the current questions that are out. So anybody else want to step in for discussion?
Yeah, maybe I ask Åke. I wanted to ask about sort of orientation of orogenic belt, and you have this rotation going from Amazonia to Baltica towards Fennoscandia, kind of. So in Fennoscandia, most of collision or compression was directed from west to east and kind of accretion. And if in your reconstruction of Amazonia and Baltica, if you kind of connect orogenic belts from Baltica to Amazonia, which seems to be oriented east-west. So what, how do you sort of explain this rotation that you show in your figures? Like it goes east-west and when it's kind of start to rotate and go to Fennoscandia.
Do you mean the rotation from Colombia to Rodinia?
No, rotation for, of Paleoproterozoic orogenic belts as a sort of, if you put Amazonia to the west of Baltica, orogenic belts between Archean blocks, they more or less go east-west, right? But but when they kind of rotate and into Fennoscandia and start to go south-north.
Well, I guess the Archean belts, I don't know if there are really any Archean belts. They are like rather small areas, so with different orientation. But if you take from say 1900 and onwards, if you take this Umi belt through western Ukraine and so on, and then take this Sweco-Norwegian or Sweco-Fenian belt and so on, they all run, say, in present-day coordinates more or less north-south from Baltica into Amazonia.
But in Fennoscandia,
orthogonal to the contact between Baltica and Amazonia.
But like in Fennoscandia itself, most of collisional belts like Kola origin, sort of Fennoscandian belt, they are more or less north-south, right?
Yeah, well, the Kola belt is more east-west, but that's another collision between Kola and Karelia, so that's another stuff. But if you think about southern Fennoscandia, then you can say that the belts are running north-south and running into Amazonia. If you look into the Sweco-Fenia is like complex because it's a big area, but it's not very elongated. So it's like Raimo Lahtinen a couple of weeks ago when he talked about this kind of buckling and everything coming together. And I think it's like the oblique collision between Sarmatia and Fennoscandia makes the Sweco-Fenian like a big pile, which is not really elongated, but it's like a big blob sitting in the middle.
The terrain wreck.
It's like like a hinge that is also bending a bit, like yeah.
Okay, yeah, maybe we can talk.
You have to have a map maybe and look at it together. Otherwise, it's difficult. I can maybe make a kind of, here comes or let's say Sarmatia as a kind of a snowplow or bulldozer and bulldozing into Fennoscandia and compressing and everything. So you have this north-south belt, but you also have like a big pile of stuff that is a Sweco-Fenian orogeny.
Thanks.
Okay, great. Anything else? Okay,
No.
go ahead, Paul.
Yeah, so is there paleomagnetic support and declinations for the rotation of Baltica relative to Laurentia between Nuna, Columbia and Rodinia?
Well, as far as I understand, the paleomagnetics, they have said since a very long time ago that there is like a 90 degrees clockwise or rotation of Baltica. And that's like always like standard cited in the literature. But if you look at the configuration, it should really be almost 180 degrees relative rotation between Baltica and Laurentia. So, or at least 100 and 170 or something. So if Baltica rotated 90 degrees clockwise, then Laurentia has to rotate something like 60 degrees counterclockwise at the same time. And I don't know if there is any paleomagnetic evidence for that. There is all this stuff talk about the Grenville loop and the Sweco-Norwegian loop, but as I understand, they are not really contemporaneous, and people are discussing in what direction they go. But one would think that one would show if there was a loop, that would be a loop in opposite directions in Laurentia and in Baltica. Then, if we are rotating in opposite directions.
I always liked Epi Hartz's Baltica upside down reconstruction. What does that do for Samba?
I think it will also completely disrupt it. It will disrupt all the traditional correlations. So I don't like it. And it's not going to be getting any much support in later years either. But
Western Baltica does not have much in common with Eastern Laurentia in terms of Rodinia, pre-Rodinia geology.
Wow. Don't you? We have you see all these things: Pinvarian, Telemarkian, Gothian, Labradorian, all the correlations you can do between the Grenville and Sweco-Norwegian. I think it's better than if you turn Baltica upside down, at least.
Well, the Neoproterozoic of the Varanger Fjord is completely different from Svalbard and East Greenland.
Mm-hmm. Yeah, that I don't know so much about what's up there, but.
All right. Should we call it there? Cool. Thanks a bunch, Åke.
Yeah, we
Good
call it
talk,
today.
good
My
discussion.
wife just came in here and waved to me or waved to you. So I guess maybe I will have dinner soon with her. So
All right.
we call it today here in Sweden at least. And you
Great,
have to
okay.
go and work in Laurentia.
Yeah. All right.
Work
Yeah.
on your
dinner.
reconstructions.
Cool. Take care, everyone.
Bye-bye.
Bye.